Good afternoon, everyone. This is DiPippo from Envision Technology Advisors. I'd like to welcome you all to the 2 p.m. webinar. It's entitled Maximizing SQL Performance, and we're going to concentrate on designing for scale and architecting for virtualization. I wanted to take a minute to talk about the topics that we put into the title. Obviously, when you look at a title, it has a certain amount of appeal, but when you piece it apart, what do we really want to talk about today? And I also wanted to put it into context on some of the focus areas that we have for SQL when we're either doing an assessment or just in general when you're having conversations or talking about architecture and design, and then some of the basic activities around those sort of goals. So we have 6 areas that we focus on when we look at a SQL implementation, either if it's for remediation or for design and architecture. One of them is always going to be performance and optimization. Another one is going to be scalability. Virtualization is, of course, a very hot topic always, but also there are a few that we won't touch on today. Security, reliability and availability, very important, and one that we like to call operational excellence, which is operations and maintenance, and that's something that tends to kind of not be as stressed as the previous 5, but something that we feel is extremely valuable and extremely important. As far as the activities go, we have, of course, the infrastructure and how that's architected and designed, and we have database and application architecture and how those are designed. And then, of course, there's the process of planning, deployment, operations, and maintenance, which just kind of forms the whole life cycle. So the ones that are darkened are the ones we're going to talk about today. Now, the goal here is to give you about a half hour or 40 minutes of content, and then to open it up for questions and discussion. Every single one of these could be a whole day talking about performance and optimization, certainly if there are specific instances of things that need to be analyzed or optimized. Same thing with scalability. There's a huge conversation that you have about where you are, where you're going, and that sort of thing. Virtualization likewise. So every single one of these could be a very expansive topic. So we're not going to go too deep into each of them, but we're going to give you a holistic view of them. So the first one we're going to start with is performance and optimization, and we're going to start at the bottom layer. The bottom layer is the infrastructure. This is the physical aspects of what's running your workload for SQL Server. So for the first one we're going to do is CPU, and it's important to note, and this kind of permeates the whole conversation, but SQL workloads differ. But there are 3 main factors that affect it. One of them is concurrency. This takes two ends, basically. Concurrency talks about the number of people that can do something at the same time. It has 2 different aspects to it. One is the number of people that can do sort of the same thing, like reads. How many people can you get in querying a database at the same time? And the other one could be a very much smaller number, but you could run into concurrency problems with people updating a database. So in either situation, you're going to affect just about everything, memory, I/O, but CPU is affected by concurrency. Even if you have a small number of things that people are doing, if there's a lot of people doing it at once, you have a CPU load issue. A good example of this is a website. So when someone goes to a website to query product data, they're looking at your product catalog. Most folks are just going to be seeing the same exact query. They're going to go looking for a product by its number. However, if you have 5,000 visitors to your website at one time, like for instance when you have a limited time offer or something like that on the table, then you're going to see the CPU is really going to spike. It has also a lot to do with the architecture of the application, but when we look at the CPU and as we're going to build the infrastructure, one of the things we have to take into account is how much concurrency will the system see. The other one is parallelism, and parallelism is slightly different than concurrency in that we talk about concurrency being multiple disparate processes that are running at the same time. Parallelism is where SQL Server can take a single process and it can split it up. So what you'll see sometimes is if you have a lot of CPUs running on SQL Server and you look at the times that they're busy, you have to look to see if it's one or the other. Is it big decision support queries that are running that are causing the CPUs to all be used to satisfy that query, or are they smaller queries that just get run on one processor, but there's thousands of them going on? And then the last one is computation. And computation is really totally dependent on how the application is architected and really what it's doing. So, for instance, things like I just said where you're going to get product data, most times that's not really computationally intensive. Now, SQL Server does a lot of computations behind the scenes, obviously, but it's not computationally intensive to want to just go find the data on a particular product ID. Some other things are computationally intensive, and one of the things we see with CPU-bound processes that have the computation element in them is that they are architected before SQL Server had some of the facilities it had in it, and the applications were never updated to take advantage of them. One of them is a good example is the merge statement, spatial data types, hierarchy type, etc. So the merge statement is one single statement that SQL Server can use to update, insert, delete records from a table based on another table. So if you have a big table of changes and you need to go update all the existing records, delete records that no longer apply, update records that have changed, insert records, you'll find a lot of applications that have a great deal of code that runs, say, in a stored procedure. And that code will be completely dedicated to doing that task, and there's a one-statement SQL statement you can run that's a merge statement, and SQL Server will take care of it behind the scenes. It is an order of magnitude at least faster. Same thing with spatial types. Anytime that there's any sort of computations around map coordinates or geometry or geography or anything like that, it used to be where we would store, the latitude and longitude as two floating point numbers and then have to do all the math inside SQL Server. So SQL Server now has spatial types that store either a geometry, a line segment, a shape, map coordinates, etc. And right in the SQL statement you can tell it, show me where this is inside this box, and things like that. Hierarchy type, same way, any parent-child relationships, etc. So I don't want to dig too far into that because that really starts to talk about the application design, and a lot of times you don't have really control over that using a packaged application, ERP, etc. But in general, if you're asking questions or if there's any possibility of writing custom code, customizations to ERP, etc., to either, or if it is a customization in general, or if you can write, say, an alternate process. Let's say the native process that comes with the packaged application has a very high CPU load when you're doing a certain activity, and if you can get a customization written that does the same exact thing as packaged functionality, doesn't seem like that would be a good idea. Usually you concentrate on things that are custom business processes, but if you can get something to be 5 or 10 times faster, that might be a customization worth looking at. And certainly for anyone that's in the developer audience, taking a look at some of these things that SQL Server now has built into it. And if you look specifically at the spatial types and if you look at the spatial types and the hierarchy type, those are examples of types that are they're built into SQL Server, but they're produced and they're made available via the ability to have .NET extensions. So you can write your own data types inside SQL Server that do computationally intensive things in a much more efficient manner than just writing them in SQL code. So again, we're talking about infrastructure. I didn't want to get too far off on that, but one of the main things of infrastructure is the CPU. One of the main things about the CPU that gets used is for computation, and one of the best ways to eliminate computation bottlenecks is to really take a look at what you're doing inside SQL Server and see if there's any better ways to do it. So the next big bubble we have when we talk about the infrastructure is the I/O throughput and storage. Now this always traditionally meant disks. So we'll talk about that in the second bullet, but I will say traditional SQL architectures require fast I/O, and there's three main things that SQL does that needs I/O. One of them is writes, and the second one is reads that are not in the buffer cache, and the third one are operations that spill to temp DB. So writes are obvious. You never want to have a write just stay in memory, so it has to hit the I/O system. When a write happens, it hits the log first, and then it gets persisted to the data files, and then the transaction commits. So whenever you're dealing with a write, you're always dealing with I/O. There's something called lazy writes, where as long as you can be guaranteed that the data is protected, it won't go back and write to the main data files, but you're always writing to logs, and you're always eventually in very short order writing to main data files. That always takes I/O. Now reads that aren't in the buffer cache are big reads or reads on cold tables that haven't been accessed in a while. Those take I/O. Reads that do hit the buffer cache, those don't take any I/O. They take computation, they take CPU and memory, but they don't take any I/O. And then the third one, which is the toughest one to track, is our operations that spill to tempdb. Now that's a SQL term that we use, and it's very interesting to note that it's tough to determine when things are spilling to tempdb, because when we take a look at the optimization and we talk about how you really have to know how SQL Server goes after the data, and once you figure that out, all of these things about how to optimize what's going on per query become very clear. One of the things is when it spills to tempdb. So just those of you that know what SQL statements look like, if you have two tables that are being joined together, if you have data that comes out of the database and it's not in the order you want, you need to sort, or there's a bunch of other operators that the query processor will use. You basically give it a request for data, it figures out the best way to do it, goes after the tables and the data files, grabs it all together, brings it back to you. What it does is it determines a plan that it's going to use to satisfy that query, and each step along the way is essentially a primitive operator. Any one of those primitive operators has the possibility of spilling to tempdb. And I'm sure that everybody that has even looked at the basic statistics of a busy SQL server see that the tempdb disk or the tempdb files are always hot. And that and the log is probably second, and then the third, of course, is the data files, because it's very, very efficient about that. So an interesting thing is that today's challenge is that storage is non-deterministic. And what I mean by that is determinism basically means that you can repeat and understand what's going on every time you run something. The problem with today's architecture is that the path from SQL through the layers to the actual physical bits on a disk is complex, and it can change as each layer exerts intelligence. And I have a diagram here. And we'll just wait for everybody to get that. There we go. That shows you what would happen. So I'm going to start here and say SQL Server File I/O. So there's when you write to a table, let's just say you're writing to a sales table, the first thing is going to be File I/O. Now the dynamic nature of this is you could have multiple file groups. You could partition the data such that it's not all in one big table. You could add multiple files on multiple spindles or multiple data stores or whatever to split the I/O up. So SQL Server itself, when you write a record, you have to first determine which file it's going to. And then the operating system is going to know where that file lives and issue the write, and then that's going to go to the operating system storage volume. So that would be, say, the F drive or something like that. Now, once you know it's writing to the F drive, then we have to know where the F drive goes, and that goes to a storage fabric. And over here, by the way, the storage volume, that could be a mirrored volume at the operating system layer. You don't usually see that, but it could be. So, depending on which one is hotter, it might use one side or the other. Same thing with the file. Whichever file is hotter, it might use one or the other for reads. And then it goes to the storage fabric. Now, whether that's Fibre Channel or whether that's iSCSI or something else, right, it usually has multiple channels to choose from, so it's going to go over the one that's either least used or available. So if you have an I/O problem, you might have a dynamic issue there because it might be in the storage fabric, and the storage fabric might have selected one path for a couple of days and then all of a sudden switched to another because something went bump in the middle of the night, or dynamically decided to switch this particular load over, etc. Then once you get to the actual storage volume, you have to know which container that's in. So then you get to the container. So this would be like the drive is a logical drive carved out of the storage container, which would be 20 disks that are in an array. So now you know where the disks are, and then you have to get to the slice. So this is something that not all storage arrays do, but many of them do. So this means that even if it's only a if it's a 1 terabyte volume and it's in a 10 terabyte array, the actual slice of that volume and array is the thing that the storage unit will decide to tier. And then you have to decide what storage tier you're in. And what by storage tier I mean that we have your slow disk, which is SATA, your faster disk, which is SAS, and then you'll have SSD in modern storage controllers, the solid state, which is much faster than either of the other two. And then from the SSD, they'll also have a whole bunch of RAM, which is lightning fast. So you've got these 4 tiers. So to know which slice of the container is in which tier at any given point is a moving target. So understand the point here is that in determining I/O for optimization, you have a real problem with it being non-deterministic, because every time you go down the stack, you not only have to decide what's the stack doing right now, but what is the stack done? Like if you had a problem yesterday and we're researching it today, has anything changed? Has are we looking at the fact that, hey, this is on SSD already, but yesterday it wasn't? So, it becomes a lot more difficult to do that, but not impossible. You just have to say, okay, we need to isolate every single layer along the way, identify what kind of intelligence it might have, and then see how we can track that and instrument it and at least audit it, see what was going on. By the way, I'm sure everybody knows, but you can raise your hand if you want me to stop or you have a question. You can chat, you can ask questions, etc. along the way. I think we could get through the slides. Again, I'm only going to go for about 30 minutes or so. Okay, so memory. The thing I would say about memory is it's a shifting paradigm. So SQL Server has many memory needs. Matter of fact, there's a SQL dynamic management view called memory grants, right? And there's also the cache handlers inside SQL. And you take a look at memory inside SQL Server, and it's just like a huge swap meet. So SQL Server allocates a bunch of memory from the operating system, and then there's just so many different components and so many different reasons that SQL Server will carve that memory up, and different components borrow and steal and everything else from each other and so on. But if you boil it down, really the two that are always at the top of the list, unless there's something wrong, of course, but two that are always at the top of the list are the buffer cache and the query processor. So the second one, folks might be a little bit surprised to see, but that actually can be pretty big in certain cases. So the buffer cache is what you normally figure. You give a SQL Server 12 gig of memory or 16 gig of memory or 60 gig of memory, whatever you give it, and you limit it so it doesn't overwhelm the system. And you figure that 60 gig is going to go to all buffering data, so you don't have to go to disk, right? Well, if you take a look, you'll find out that the query processor is stealing a whole bunch of that. And that's because every time you issue a SQL statement to SQL Server, the query processor goes in, it parses it, figures out what you're asking for, and then it builds a plan. And in the process of building a plan, it does things like it'll build a whole bunch of plans and kind of do a what if and figure out what the best plan is. And there are all kinds of settings you can tell SQL Server how deep to go. There's a there's a concept that SQL Server could spend so much time analyzing the query plan that it spends so much time doing that the gains it made in finding the absolute optimal plan were actually consumed by the time it took to find it. So SQL Server kind of has a bailout. It says, I'm going to chew on this problem to find the best plan for a little while, but at a certain threshold, I'm going to say I probably have a good enough plan, and if I spend any more time, the incremental gains will be too small. So there's a lot going on, and it's really intelligent, and we're gonna actually see what the query processor does, kind of as a visual demonstration, and then you can understand why it needs so much memory. So anyway, when you talk about memory, usually it's what's in the buffer cache and what's the query processor doing. So if you have an application that has a lot of stored procedures, which are all templatized, the query processor is probably going to be pretty lean. if you have an application that just builds a lot of SQL statements on the fly and sends SQL Server a bunch of new queries that are basically the same query but things in a different order or whatever, a lot of garbage in the query processor, honestly, from application developers. But if you look at it, you'll see that, hey, like literally we've got 250,000 query plans that SQL Server has built up since it was last rebooted. That means that there are 250,000 different requests for information, not different requests for slightly different information, different formed requests, probably the same question asked 30,000 different ways, that gets the same result. So that's something that we look at. And as we look to build for scale, as more and more people start using the system, you have to know where the memory is going. By far the most interesting thing to say about memory is that modern advancements in database design and database technology they're introducing a third use of memory, which will actually dwarf the other two when it comes right down to it, and that's in-memory technology. And this isn't just buffer enhancement. It's not just a new and better way to buffer data. It's a complete paradigm shift. I don't have a diagram for this, but let me just kind of explain to you the difference. If you take a look at how databases have been architected since the 60s, to be honest, the 60s since mainframes, you always said to yourself, well, we've got this really slow spinning disk, spinning drum it was at the beginning, right? Spinning platters. They can't spin too fast or the head will crash into the platter and make streaks. That's head crash, right? That's where the term first came from. Anyway, you go all the way back there and you see that the whole paradigm was, okay, we got this really slow disk, but that's where the big storage is, right? That's where we can store our big data. And what we want to do is we want to figure out a strategy of how to store it and then how to use this very, very small, expensive, but very fast memory to make the storage faster. So that's the paradigm, right? That's caching, and that's essentially what we've been doing on a whole bunch of things: file caching, disk caching, etc. Database caching uses, as I said, it uses the buffer cache, the buffer pool, to selectively load blocks from the database. They're called pages in SQL Server, or extents. So a page is 8K, an extent is 64K. So if you look at the buffer pool is a series of 8K pages that came from the disk. So what are in those 8K pages? Simply whatever was needed from disk that was needed most recently. So it's a queue that essentially ejects stuff that it doesn't need anymore, or in lieu of stuff that's needed right now, and it keeps things in as long as it can. As a matter of fact, there's a performance statistic called the page life expectancy that you can look at in Performance Manager. And in Performance Monitor, you want to see that to be like 5 minutes. And there's a calculation you can do as a DBA or a systems admin that says, if my buffer pool is 24 gig, right, and the page life expectancy is a minute, that means that if you read a page into the database, a minute later, there's so much going into the buffer pool that that page needs to be ejected, so it only lives there for a minute. Well, that means that over the course of a minute, you're loading 24 gig. That's probably not an actual example, because I/O would be bound by that. But if you look at it, that's why we like to see pages at 5 minutes or more. So you load something into the database, and if the page life expectancy falls below 300 seconds, you got a problem. But that's the calculation you can do. You can say, I've got a terabyte of memory in this SQL Server, or I've got 16 gig of memory. So the calculation can be much different. And all you have to do is see the life page expectancy and say, hey, that means my buffer is turning over that fast. So anyway, that was the whole paradigm, right, of trying to, all of that discussion and all that technology and all of that monitoring and whatnot is about the buffer pool just being a reflection of what's on disk to make it faster, with no regard to what actually is in each page, except that it is needed right now. In-memory technology is a complete rethink of that. So disk is really slow, but that's okay because nothing really lives on disk. Things live on disk only because we want to be able to be protected from a power loss. As far as we're concerned, unless there's an update to the database or unless we're restarting, whatever is in memory is where that table lives or where that data lives. So again, it might seem like it's just an enhancement to buffer pool technology, but it's a complete rethink, because the way that SQL Server actually goes after the data in memory, I'm not sure if everybody is the right audience to know the word B tree, but data in a SQL Server index is stored in a B tree. It's a data structure that was developed specifically for long-term storage like disk, and it's a way of architecting data such that the B tree will always be balanced and quick to access and efficient to buffer in memory. B trees are gone in in-memory technology. In-memory technology structures things the fastest way they have it today, and that is in 2012 and 2014, is a hash table. And there's also something called a BW tree, which is a way of architecting data in memory such that it understands that, hey, I'm in memory. I'm not dealing with I/O channels. I'm not dealing with spindles. I'm not dealing with SSD. I'm dealing with memory, and I'm dealing with CPUs and possibly NUMA nodes. So anyway, there's a lot going on within memory technologies. It's really exciting. So our next slide, until everybody gets that. When we talk about the database and application design, and even really just performance optimization, what we look for is we want to understand how the layout and processing optimizations come from an understanding of how SQL satisfies queries. So let's take the lineage of an activity you would do. So someone has a report that gives a customer list for a given salesperson, or in my example, a state. I want to see the salesperson and the customer for a given state. That report is fed by a SQL query. Now, whether the query was written by a human being or the query was written by a tool that someone used in Excel or something, eventually it winds up as a SQL statement in SQL Server. That SQL query is satisfied by the query optimizer and processor. It parses the words, figures out how to go after the data. But then the query processor and the storage engine talk together the same way you used to when you wrote programs for what was called ISAM, which came before SQL Server. So if you just take a look at this example, this is a SQL statement. Anybody that's seen them knows what these look like. So this is basically going to grab the salesperson name, customer name, and state, and it's going to use this structure where it has salespeople, then it has a table that it knows which salesperson is assigned to which state, and then it has a table of locations, and it knows which location belongs to which customer, etc. And then it's going to get it by state and then get it by name. It's going to get it for a state and then order it by name. So there's a lot going on here. It's going to do a select distinct, right? I'll go from the bottom up. So first thing it's going to do is it's going to go after all four of these tables and kind of find out first. It's going to get the location that's Rhode Island, so it'll start here. And then it's going to grab the salespeople states and go up to salespeople and then grab down to customers, etc. And then it's going to get the result set that works with. And then it's going to assemble these four. That's three. It's going to assemble these three columns, and then it's going to make sure it only has distinct rows. So if the same salesperson has the same customer and they have 5 locations, say in Rhode Island, I only want to see that once. So it's going to do a distinct, and then it's going to sort. Now the order in which the tables are accessed, the order in which this is applied, the order in which it does the distinct versus the sort, etc., all of that's done by the query optimizer and the query processor. But at the end of the day, all of the magic it does, this is really great. I mean, this to some folks might look like programming, right? But programming in the old days, and I'll show it to you in the next slide, was a lot different. So now all you have to do is send SQL Server this, and it sends you back a row set with these 3 rows in it that basically match the query you asked for. This is why you can take a tool like, say, Excel or whatnot, and you can have a WYSIWYG interface that a normal user can use, and it can then assemble some dynamic SQL like this. And this, by the way, ties back to the other statement I made, where if the tool doesn't adequately templatize or doesn't do this consistently, you could have 2 different people use the GUI tools to ask for the same exact information, and it could generate dynamically 2 very slightly different SQL statements. But according to SQL Server, it has to parse those individually. But anyway, that's all the magic of the query processor. So to show you what happens, though, let's say this is the physical reality of how the data is laid out. You got a salespeople, you got a table that says which salesperson has which state. you have a list of locations and then which location ID is which customer, etc. So what SQL Server would do is it would want to go and find all the Rhode Islands, but seeing as how this is a big table, it would probably use an index that had it sorted by state. It would find that it's location 1 and 2. It would find locations 1 and 2, and then it would find that Rhode Island is also John, and then it would find location 1 and 2 are both customer 1, so it would bring back this row twice, and because it has a select distinct, etc. So everything I just described with the laser pointer, that is the way you used to have to program things. You used to have to say, open up this index, seek to Rhode Island, find this, go get this, etc. So SQL Server abstracts that quite a bit. Now, the whole reason for going through this is to say that even though we are so much further ahead of having to write 40 lines of code to get this report to run, if anyone remembers RPG or any of those old programming languages, instead of having to write 40 lines or 400 lines of code to get this report to run, we can just run a SQL statement, or better yet, use a GUI tool that dynamically creates that SQL. The problem is that you still have to know, after all is said and done, after all the magic is done, how is SQL going after these things? And that's when you say to yourself, well, that's not going to work, because SQL's scanning this whole table, which might have this other info, might have all kinds of stuff that it has to sift through all the time, you know, using pages in the buffer pool to store all this data that we really don't need. We don't even need the location name. We don't need any of it. We just need the state. So that's where SQL Server, if it has a good index, can be much more efficient, etc. So again, the summary statement is that to really be good at the processing and optimization of the processing of a query, you kind of have to be able to go from wherever you are, an operation in an application, like looking up a customer. You have to be able to trace how that's getting through the system and which SQL statement is actually getting formed and executed to satisfy that request, and then how the query processor is going after the actual data. Because at the end of the day, it's on disk, it has to be read from disk, right? So at the end of the day, there's no magic beyond that, and that's what we have to understand. Okay, so let's move on. If anyone has any questions about that, you can let me know. You can raise your hand. But that's what we're going to say about performance. So the next thing we're going to talk about is scalability. And honestly, scalability has two main topics. You can talk about scaling up, or you can talk about scaling out. Just sort of a general definition is that scaling up is the ability for a monolithic entity, i.e. VM or server, to handle an increasing workload. Scale out is the ability to distribute an increasing workload to independent, coherent entities. And when I say coherent, independent means they share nothing, preferably, right? And coherent means that they have some sort of a ability to keep themselves up to date. Because obviously you could scale out an ERP by having two completely separate ERPs, but if they don't share customer data or sales data or anything like that, it would be, you know, a ridiculous scenario. So it has to be coherent. There are some cost considerations when you talk about scale up versus scale out. I think that if you look at something like Hadoop, Hadoop is the king of scale out, right? The whole idea of that is to have these off-the-shelf servers that you can buy, or even off-the-shelf desktop machines you can buy for $300 a piece. So if you bought a really, really big server for 30 grand, you know, you could buy 100 $300 workstations for that, right? So if you had 100 different $300 workstations with a really fast dual-core processor, and you could scale out that workload, you know, you have much more than you would have if you bought, because you got 200 cores, right? If you try and get 200 cores in a scale-up server, you're probably spending more than 30 grand. So there are cost considerations, though. The acquisition costs differ from operational costs, and they usually hit a different budget, right? So a $50,000 server versus 10 $5,000 servers, they might be an equivalent capital expenditure, but obviously they're much different operationally. So we won't dig into that too much, but when we talk about whether or not we want to press either an application's configuration or a design for an application to be able to scale up or scale out, it really has to do a lot with the workload, a lot with the cost structure we're going for, etc. Okay, so the next topic is just to talk a little bit about scale-out technologies for SQL, and these could be pretty deep. but these rely heavily on the ability of the application to scale out. They're increasing order of dependence on the application design. So the first one is always-on technologies. This was renamed in SQL 2012. So 2005 and above had log shipping, it had replication, and it had database mirroring. And these technologies were all about being able to have multiple SQL servers have the same data. Some of it was for scale out, some of it was for recovery. But especially in 2005 and above, you were able to do things like have a log shipping secondary that was readable so you could run reports against it, a database mirroring secondary so you could run reports or even backups against it, etc. This is now called always-on technologies. The problem with those is that in 2005 and 2008, they were heavily dependent on the application being able to say, all right, I'm going to write to here, but I'm going to be able to read from here. Even with database mirroring, you had to have a SQL server that could understand the failover partner. Otherwise, if the main SQL server went down, they were usually accessed by name. You'd have to wait for a DNS update or something like that before it would automatically fail over to the other. The always-on technologies wrapped in all of that stuff and also added something called database availability groups. Database availability groups came from Exchange, actually. They share technology. They share technology with the cluster, Windows clustering, and this allows you to actually have up to a certain number depending on the service pack you're on, but you can have a primary and a certain number of secondaries. The secondaries can be updatable, and they also follow with clustering where if one fails, the other one can be brought up and it has the same exact name. So applications can be a little bit less aware that they're on a database availability group, and that works pretty well. The other thing you have is replication. That's been in SQL Server for a long time. You got several different types of replication. You've got transactional, you've got merge replication, you've got snapshot, and this is all about keeping multiple copies of SQL Server up to date. This depends a lot on the application because certain applications are not very friendly with having the data change underneath them. So let's say you have no writable secondaries, you have one master store and you have it replicated to 4 other servers that you point people to do something at the application. If the primary gets an update and then goes to the secondaries and refreshes their tables, a lot of times applications will break. You'll have to shut them down, start them up again, etc. Merge replication requires triggers to be added to the database, which if you have an application that has a lot of triggers already that are specialized, that can interfere, etc. So, transactional replication and merge replication and all of those, they work really well. Most of the time they're transparent, but they do depend on whether or not the application is replication friendly. Another scale-out technology, which is actually my favorite when I talk to application developers that are building new applications, is the service broker. And that's the ability for SQL Server to go from transaction-based to transactional message-based. And this is a whole topic in and of itself, as I have said many times, but just picture it this way. A main SQL server is the one that brokers requests, or you have multiple SQL servers that broker requests. Those SQL servers update data in a very small way, but then send messages out to the service broker. And the service broker runs on every SQL server, and it's basically a message passing mechanism where a SQL server will route messages between different instances of SQL Server, and when they get to a destination instance, they can automatically start a stored procedure to finish the process. So the reason this is great is because you can have 15,000 updates, say, that come in. And if it's architected to use the service broker, that's 15,000 messages. It's not 15,000 updates to try and hit the same table at the same time, same disk at the same time, etc. So those 15,000 messages, they get queued, they get brokered out, and then they'll get executed, and all the updates will happen. Now, obviously, the application has to take this into account, and if anything needs to happen in real time, you have to identify how big the queue can get, etc. But just in case you've never heard of these three, those are the scale-out technologies of SQL Server. Now, when we talk about scale-up, we talk about scale-up strategies. And when you talk about scale-up, all you're talking about is more, right? And this is kind of in the second half there. But the main thing when we scale up is we want to optimize for concurrency. Because when you say scale up, unless you're talking about making your database bigger, you want to double your storage or you want to double the size of your database, that is usually pretty easy to do, right? Now, if you triple the size of your rows and your queries are going to, have be cubed in the amount of time. So if you have a 10-minute query and you're going to triple your rows and suddenly it becomes a 1,000-minute query, right? That's a different problem, not concurrency, that's volume. But most time when we talk about scale up, we're talking about optimizing for concurrency. So what we want to do is we want to minimize the structural coverage for a query. What that means is, if you remember that table I showed you earlier, when you look at the list of, let's see if I can find that really quick. Yeah. When you look at this, when we say minimize the structural coverage of this table is the whole table. So if we just want to go after state and know the location ID, then we want to go after this. So that's where we say we want to minimize the structural coverage of the query. And then another thing that I'll just throw out there is the use of snapshot isolation. So these two combined will allow greater concurrency, because if you're not covering a whole bunch of data that you don't need to, then you don't have to lock or latch it. And if you're using snapshot isolation, you can actually have people reading data that you're updating, and you don't have all the locking problems that you normally have. Snapshot isolation actually uses tempdb, so that's another concern, but again, that's a whole conversation in and of itself. Now, here's the thing about scale up. It's really important to essentially monitor aggressively, and that's honestly what scale up planning and scale up design is all about. You have to be able to monitor. You have to have performance statistics that are historical, that are granular, that you can explain and whatnot, because the what of scale up is not even a discussion. You're talking about more of something: CPU, memory, storage throughput, etc. The why is what's key to success. So we need more memory because our buffer pool is getting really hammered. Or we need more CPU because we have 8 CPUs and they're always at 90%. Well, why is that? So we need to know why. We need to know which queries are spiking the CPU. We need to know what the CPU is doing, etc. So monitoring aggressively is something that I can't stress enough. If you're going to scale up, and really anything for operational excellence, but if you need to scale up, the understanding what is going on in SQL Server that's causing you to use the resources that you already have, or even if it's not a problem but you're planning for growth, to understand what your usage model is right now, it's really, really key. Okay, so let's round the corner here with the last topic, and this is virtualization. So virtualization is great features, and it's also still a great debate. So there's just a debate of whether or not you should be running SQL servers on physical hardware or virtual. So that debate, which has raged for a long time, and you might think it's over. You might think that virtualization is just something that everybody accepts as being perfectly acceptable for a SQL server. But for high I/O and really high usage servers, there's still a debate. So the physical-virtual debate essentially comes down to one question: is it performance or is it flexibility that you need? Now, when we talk about performance considerations, the first thing to note is that performance is even less deterministic in a virtual environment, because it adds layers, and those layers have intelligence, and that intelligence causes variability. And then virtualization always incurs overhead. That's fighting words for some folks, but the fact of the matter is, if you dig all the way down to the actual processors, from Intel, from AMD, etc., they now support virtualization. Anybody that's worked with a server knows you have to turn it on, right? Otherwise, hypervisors don't work. Well, that model of the processor running, it incurs overhead. So every instruction that you run and every memory access you have, it's really efficient. They've done a lot in hardware and whatnot, but there's just no getting around the fact that physically there's more electrons moving in more places when virtualization is on than not. So the summary, though, that we found, and this is where the bar just keeps moving and moving every year, is that except in very specific circumstances, both of these factors tend to not weight nearly enough to overcome the benefits of the flexibility that you get with virtualization. So I say that very specific circumstances, I've seen some. So I've seen, where folks are doing a lot within memory. Even in 2012, we had the column store index introduced in 2012, and certainly people that are working with 2014 That's in CTP2, Customer Technology Preview 2. Folks that are working with in-memory tables, they're building environments that are 128 gig, and that's a test environment, proof of concept, and the server they'll actually buy will have a half a terabyte of memory in it. So you run into VM limits at that point. Same thing with 192-way huge NUMA boxes, specialized hardware, etc. So there are, there's a SQL server that I've worked on that it takes 42 minutes to start. When you reboot it, it takes 42 minutes, and that has nothing to do with anything broken. It has to do with the fact that it has so many NUMA nodes and so many cores and so much memory to configure and whatnot that it takes 42 minutes from the time it starts to the time SQL Server is running. So, you're going to virtualize that one? I think not, right? But except in very specific circumstances. So, let me just show you that first one we had. We had that thing where I was showing you the non-deterministic factors all the way down. Well, in a nutshell, if you take this storage fabric, when the operating system goes to the storage fabric, and really even up here a little bit, but basically you got the hypervisor overhead, which, like I said, is the overhead that you're going to get no matter what. When you virtualized, you got overhead, processors running in a different mode, etc. Then you got the resource scheduler, and this is where you can virtualize a SQL server in a lot of cases and have it running alone on a virtual host, and it's still worthwhile. And you'll see that in the next slide. But then once the resource scheduler actually allocates resources to the VM, then your writes are actually going to a file. So SQL writes are going to a file, and then they get to here, and then they're another file. And then the virtual host has a volume, and then that eventually gets to the storage fabric. That's the actual storage fabric, not the virtualized one, and it goes down. Now, remember we were talking about this being dynamic, all of these up the line. Well, this is the same way. So if the resource scheduler says, hey, I'm on a hot virtual host, you could suddenly be vMotioned or live migrated to a different host. Same thing with a volume file. If it's on a hot volume, it could be storage vMotion, or it could be storage migrated over to a completely different volume. And then you got the virtual host volume, which has multipaths that go through here, load balanced, and then you got all the other intelligence. So again, it's virtualization does add complexity, and it adds overhead as all these layers get added. But it also adds intelligence, as we'll see. Okay, so the next slide, I just wanted to give you guys 6 of these considerations for virtualization. Again, I think that these things weigh extremely heavily towards virtualizing SQL Server loads. First one is templating. You can bring up new servers quickly and easily with tools and automation support. If you want to try something new, or if you have the ability to scale out, or you want to bring up a mirror, a brand new clean mirror, etc., you can use templates to do that. Servicing is something that I think is one of the best things about virtualization. If you're on a physical hardware and the physical hardware is experiencing issues, you have one option, and that's to fix it. I guess you have another option, which is to buy it, a whole new one, or bring it down and have someone service it. But with a virtualized environment, you have the ability of moving things, migrating them from one host to the other. You can do snapshots where you can test application, database, and operating system upgrades, and you can revert easily, etc. Migration is also great, because if you want to take advantage of a brand new processor or a faster memory system or faster storage, hardware changes rarely require VM changes. We've seen VMs that were built originally on SAS 146 gig volumes, and that same exact VM has now been migrated 4 or 5 times, and it went from 4 gig fiber channel. It's now running on a 10 gig iSCSI environment, running on SSD drives, and the operating system didn't even know the difference. Monitoring is also something you gain from VMs, and the reason you gain that is they introduce out-of-band monitoring, and it limits the observer effect. The observer effect is a concept in physics where you can only measure something to a certain degree of accuracy before you actually start to affect the actual measurement. So in other words, if you're measuring the temperature of something, you can only measure it to a certain degree of accuracy before the process of trying to get a more accurate reading actually changes the temperature of what you're trying to read, right? So that observer effect is the same with monitoring. Sometimes when you're looking at monitoring and you see, well, what's the thing that's using the most CPU, and you have to subtract out Task Manager, right? Or you have to subtract out what you're using to actually monitor the performance. So you get this idea of out-of-band monitoring where it can show you holistically, hey, these are the number of virtual megahertz that the CPU is using, or this is the I/O that it's using without requiring any I/O itself. You also have the ability of tiering. It's another level of dynamism through the intelligence at the hypervisor layer, and that's where I was saying if it's on a hot host, it can migrate the VM. If it's on hot storage, it can migrate it at that layer. And then backup recovery is one of the other huge ones. I mean, being able to take a snapshot of the entire running VM and have it, that's what you're backing up. And not only that, having, even if it's not in an environment that could handle the full production load, just being able to boot it up and to get people on it to even read or whatever is just really a phenomenal thing that virtualization adds. So that's the presentation. I guess that went 50 minutes, not 30 or 40. But I hope that was valuable. Again, there's a lot of those topics that certainly warrant webinars of their own. But in general, these are the things that we use, and these are the things we look at when we're designing for scale and performance, and especially when we're architecting for virtualization. So on that note, I will open this up for questions. If anyone has a question, I think you have the ability to ask it right there on the, or raise your hand if you want to ask it. All right, first question is column store indexing. You tell more about column store and what's coming in 2014. Okay, so that's actually a two-part question. The question is, can I talk a little more about the column store indexing, which came out in 2012, and what's coming in 2014? That's a pretty long discussion, but let me see if I can pull something up and show you something. Okay, and I think column store is on page 30s. There we go. All right, so really quickly, the way that data is normally stored in SQL Server is it's stored row-based. So a row, let's say a row has like the location table that I showed you. Let's say that a row has 300 bytes. So a page is 8K, you take out overhead, you divide it up. That's how many rows fit on a page. So if you're looking at just getting a query of a couple of the columns in that row, SQL Server has to read the page that has that many rows on it, and that many rows has that many bytes that are in the buffer pool. You can get around this a little bit with something that was introduced in 2008 called included indexes, or included columns on indices. That's where you can create an index that just has it by the order you need, by the way you want to look it up, and you can also add a couple of columns in that you need for the result set. The problem is that doesn't really help you for generalized queries, because you have to have an index, and your storage for every case, and your storage requirements go through the roof. So what column store indexing does, it says, okay, what we're going to do is we're going to start rethink the storage model. And as you can see, what it does is it takes the table, and this is a 6-column. Let me make that a little bigger for you guys. Okay, great. Yeah, so it takes six columns in a table, whatever those columns might be, and the first thing it does, it says, okay, the storage unit is going to first start with the 6 columns. And then it actually does something else where it takes those 6 columns and then it divides them into row groups. And each row group and column intersection is called a segment. And how it does that and what it stores in each segment is, obviously the column is per column. The row group is something that is dynamically figured out by SQL Server as part of its optimization algorithm. But bottom line is that a certain column for a certain number of rows is a segment. So then when you run a query, we'll take a look at this. So this is a good idea of the 6 one, okay? That's an idea of the order, date, product, store, region, quantity, and sales amount. So the first thing that it does is it partitions it into row groups horizontally, and then it partitions it into columns, which is now segments. So you see there's 2 segments with order, date, etc. Then when you look at how it stores it, again, this is an in-memory technology. So it compresses it, and it compresses each segment as much as it possibly can so it can get as much on disk as possible. Remember that it doesn't have to keep track of what's where on disk. All it has to do is load it in, and then it uses in-memory processor instructions to figure out the rest. So then when you do like this statement right here, when you do a select on this, basically it'll get rid of all those segments. It'll only load these 9 segments and then satisfy your query. Now keep in mind, when you have a very wide table, this segment elimination can be much more drastic than just half the data. This segment elimination can be, eliminating 90% of the data that you don't need. And it also can be loading in all this compressed stuff, uses the processor to decompress it, explode it back up, and then you've got a query that runs like 100 times faster. So now it fetches only the needed segments, and let me see what we got. Okay. All right, everybody can see that. And so then, and now it can do things in batch because it knows it's just doing the read to disk and decompress, and so then it can process things in batch, say 1,000 rows at a time. So, I think that they're talking about 7 to 40 times reduced CPU time. This is actually from a tech ed presentation this year. So anyhow, that so that's a 7 to 40x CPU time. The actual query execution time, you're seeing 10 times, even up to 100 times, 80 times. It's really drastic when you have column store indexing set up. So we will, we'll make available the slide deck, and we're recording this session as well. There was another question that came in, so and then I'll continue answering the first question. So, all right, yep. So that's the column store indexing, and again, this is in 2012 and above. It is a BI version or Enterprise Edition only, so that's something that you should know. 2014 does add some features to this. It adds the ability to have updatable column store indexes. Because column store indexes aren't interested in disk, they're interested in being in memory. The quirk with 2012 is that when you build a column store index, if the data changes, the index doesn't change with it, which means that it's completely inappropriate for operational data. What it's for is it's when you have like the end of the day, when you're running reports, or if you're loading stuff into a data warehouse. Usually you drop the column store index, you load your data, you rebuild the column store index, and then it's ready to run all the reports. This obviously is something that was only temporary, and they have an ability to update the column store index. And they don't update it actually. What they do is, I think there's a slide here. Yeah, what they do is they have the original column store index, and then they store notes of what's been updated. They have a deleted bitmap, so they know what not to fetch back, etc. So they can do updates. This was actually in 2012 PDW, which is Parallel Data Warehouse, and it's now generally available in 2014. So for the in-memory technologies, in the interest of time, I'll just show you a slide and we'll go from here. Let me see what we got the best. They're in-memory tables, they're called. They don't live on disk except to, here we go, table creation process. They don't live on disk except to make sure that they're available after restarts. So there is, obviously, they're transactionally consistent and they're durable if you ask them to be. You can ask them not to be, but generally speaking, most people want them to be. So when you do the create table, just like you did before, it's kind of interesting because what happens is it actually writes a C program, a little C program. It invokes the Microsoft compiler to compile that to a DLL. It then loads the DLL into the SQL Server process, and you have effectively, by creating an in-memory table, created a little piece of code automatically that got compiled loaded into memory, and it's just like a little module that's running in the program that just is just about your table. So that really shows you how it has really nothing to do with allocating a certain amount of disk space and inserting into B trees and all that. It has nothing to do with that. It has to do with, this is a memory structure, and it has its own little DLL with functions on how to get data, insert, update, all that. So it's really a complete paradigm shift. The result of this is going to really be drastic, because you're not talking about now being able to satisfy a query in 100 times. You're going to be able to talk about really literally millions of times faster for certain things. Obviously the design of the application has to support it to get that sort of increase, but even with applications that have no changes at all, as long as they're not using the things you can't do with an in-memory table, you can take a table, make it an in-memory table in 2014, application won't know the difference. So let me highlight that a little bit more, just a second here. There are certain things that you can't do with an in-memory table that you can do with a regular table. I won't give you a list, but you can look at it. It's called Hackathon or In-Memory Technologies for 2014. There's restrictions. So if you have an application that does some of those operations with a table, you can't make that table an in-memory table. But if you have an application and you can be reasonably certain, or at least you can test it, that it doesn't do any of those, you can make a table an in-memory table without the application even knowing it. And the only thing the application will know is that that table suddenly is lightning fast. So this is very exciting. But this is where I say, used to be, let's get the buffer pool and let's get 32 gig assigned to this buffer pool. Now it's going to be, well, I have a table and it has, 30 gig of data in it, so I need 30 gig just for that table. So you're going to see memory really, really balloon. Okay, do we have any other questions? SSDs. Let me read this one. All right, just one more question. There's a question about SSDs and storage and whether that still works for SQL and whatnot. What I would say about SSDs, there was a concern earlier on about write leveling, because the fastest way to burn out an SSD is to put it on the wrong usage characteristic for SQL Server. If you put your tempDB, for instance, or your log volumes on an SSD drive, within a year that drive's gone. You're never going to really do that now. I mean, a lot of the dynamism we were talking about in the storage architecture is that the storage will actually figure out which tier things need to be in. And it usually has 4, right? It has cache, then it has SSD, then it has SAS, and then it has SATA. So, it'll figure out where to put it, and it deals with the right leveling at that level. So there is no real problem with using SSD. There's a lot of SSD only, or mainly SSD, like Violin Memory is one of them, and then Tintry, which actually the Envision in-flight cloud, which is our cloud platform, we use Tintry storage for the high-performance storage backing up VMware, and that is, that relies much more heavily. It's not just SSD accelerated; it's built around SSD, and again, it's just built with the magnetic disk just to have overflow and whatnot. The other thing to note about SSD is because your investment in SSD on the storage level is so much controlled by the storage level and not necessarily SQL optimized or available to SQL Server for direct decisions. SQL Server in 2014 does have a buffer pool extension for SSD. So what you can do is, if you had a couple of SSD drives and you just dedicated them to SQL Server, and doing this in a virtualization environment is a little bit different, but essentially dedicate non-volatile SSD drives to SQL Server, it will use them as an extension to the buffer pool the same way that a smart storage array will. And the way it does that is right here. Let's see if I can. By the way, just for the other question, I'm not sure if I can release these slides to you. They're on the recording, so you got them that way. But this is actually something I got from TechEd when I was staffed it this year. So I have to check the NDA on this. but I doubt it's on the NDA anyway. But I'll check. So anyhow, this is the random IOs to mechanical drives, right? You've got database tables. I'm sorry, you got the RAM going in. You got all of these things happening. This is basically your normal flow. Then when you do the offload to SSD, you notice that this whole thing no longer happens, right? So you're basically doing the log sequential to keep the transactional consistency, but SQL Server is using the SSD for its own purposes. So anyhow, that's probably not really good justice for the SSD capabilities of SQL 2014, but just note the basic theme there, if you're going to research it, is that using SSD to bolster your storage architecture is under the control of the storage, and that can be dedicated or at least weighted towards SQL Server. But SQL Server 2014 also has the ability of directly controlling SSD and making decisions that are best for it. So, all right. Are there any other questions? Okay, well, we're about 6 minutes over. I would like to thank you all for coming. I'd like to thank you all for attending. And I hope this was informative for you. And if you would like to talk about any more of these things in depth, or anything related to SQL Server, if you want to see some demos of the column store and the SQL 2014, we have environments set up for that, etc. So I hope this was informative for you guys. I thank you again for coming, and everyone have a wonderful day.